We come to the section 6. Section 6. The students are able to understand the differences of theorems, ideals, etc. So, now if we what is also we know the definition of field, subfield. We know the difference in ring and field. So what is field in case of a ring? Say suppose Zn under addition and multiplications. Zn under addition and multiplication is an integral domain. Hence, a field if and only if n is a prime. If and only if n is a prime. So what is case? Simply I say in a standard, Zp is a field. Zp is a field. Zp is field means P is a prime. For example, Z5, Z7, Z11, Z13. These are all a field taking non-zero elements. For what is Z5? We can take 1, 2, 3, 4. Z7 take so 1, 2, 3, 4, 5, 6. So here each is a commutative, okay, as a unity. Each element possesses a multiplicative inverse. Each element possesses a multiplicative inverse. Suppose examples 3 into 4 is a 12, like that. Each suppose if you take it in the table form, each 3 as inverse, 4 as inverse, 5 as inverse, 6 as inverse. For if you take that Z7 like that. So if you take a table, suppose 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 2, 4, 6, 8 is 1, 8 is 1. So 10 is 3, 12 is 5, 12 is. For example, if you take, so 1, 2, 3, 4, 5, here 2 is the inverse of 4, 4 is the inverse of 2. 2 is the inverse of 4, 4 is the inverse of 2. Here 2 into 4 is equal to 8. 2 into 4 equal to 8. We can write 1. Z7 we can write it 1. Remainder is 1. Similarly, if you take 3 into 5, what's the 3 into 5? Is a 15. 15 can be written as 1. Yeah, 3 is the inverse of 5. 5 is the inverse of 3. 3 is the inverse of 5. 5 is the inverse of 3. Is 1 is negative. So yeah, it's a Z7 as a commutative, as a unity. Each element as a multiplicative inverse. For example, 2 get inverse 4, 4 get inverse 2, 3 get inverse 5, 5 get inverse 3. For example, 6 get inverse 6 itself. 6 inverse. And now, so as a each element as a multiplicative inverse. So in Z7, Z5, like that. So if we take a simple Z5, 2 into 3, 2 into 6, 6 it can be written as 1. So 2 is the inverse of 3, 3 is the inverse of 2. So each element has a multiplicative inverse. Each element has a multiplicative inverse like that. So we shall first show that Zn is integral domain if n is a prime. First we shall prove n is not a prime. First in case if n is not a prime, so n is not a prime, n is composite. If n is not a prime, n is not an integral domain, or n is a composite number. If n is a prime, then as a zero divisor. You know the meaning of zero divisor? A into b. A not equal 0, b not equal 0. So a b equal to 0 is a zero divisor. Yeah, when if n is not a prime, n is not a prime, a not equal 0, b not equal 0, a b is a 0. Is a zero divisor. Now n is not a prime means n is a composite. There exists two integers. So n can be written as product m into l. Suppose if you take m into l. For example, suppose if I take a 15. 15 is not a prime. 15 can be written as 3 into 5. 3 into 5. Here, 3 conditions. 3, certainly 1 less than 3 less than 15. Suddenly 1 less than 5 less than 15. Yeah, the divisor will always less than that 15. See, 15 can be written as 3 into 5. 3, suddenly 1 less than 3 less than 15. 1 less than 5 less than 15, like that. So n equal to ml with 1 less than m less than n, 1 less than l less than m. So here n not equal to 0, m not equal to 0. Yeah, the product should be a 0. Here the 0 divisor. Product a not equal to 0, b not equal to 0, ab equal to 0. If n is not a prime, keep it in. N is a composite number, I am saying. N is a composite number. So this implies that m is a 0 divisor in Zn. M is a 0 divisor in Zn. This implies Zn is not an integral domain. This is the definitions of integral domain. Z is not an integral domain. Is Zn is an integral domain, n must be a prime. N must be a prime. We have proved in the previous session. In an integral domain is a field, and every integral domain is a field. So that's why I'm using. So here integral domain is a field. Yes, not an integral domain, it's not a field. So in other way, conversely, we shall show that n is a prime. This implies that Zn is an integral domain. It's sort of is a true. Zn is an integral domain if n is a prime. So we come to the multiplication in Zn cross under multiplication is a commutative ring with unity. Yes, is a come to the definition of a field. Commutative as a unity. Commutative as unity with unity. It is sufficient to show that n is a prime. This implies Zn has no 0 divisor. Zn has no 0 divisor. Not 0 divisor. A not equal to 0. B not equal to 0. The product AB not equal to 0. Without a 0 divisor. A not equal to 0. B not equal to 0. Product AB not equal to 0. I have one of them. This. So let A not equal to 0. B not equal to 0. A B equal to 0. For some AB in element in Zn. AB is an element in Zn. This implies we can A not equals B not A B can be written as n is a product of AB. A divides B, B divides B. A n can nk. Suppose if you take A B is equal to nk. A B is equal to. This means yeah, k this for some k is an integer. K belongs to some integer. This means n divides A into B. We know divisibility. N divides A B means n divides A or n divides B. Why? This is a prime. So suppose we can write n divides A, n divides B. So if n prime means that 7, for example 7. What is 7? 1 into 7. So 11, 1 into 11. So 11 can be 1 divides 11. So like that. So 1 divides n, 7 divides 7, like that. If A prime, if one of them is divides, means n divides A, nor n divides B. N divides B. If A equal to 0 or B equal to 0, any one of them is 0, the product is 0. A cross B equal to 0 in case of n is prime. So A equal to 0 or B equal to 0, hence Zn has no 0 divisor. Therefore, it is an integral. Again, I come to the definitions of integral domain. Zn has no 0 divisor. Therefore, it is an integral domain. Further, see, you are holding the definitions. Every integral domain is a field. Every integral domain is a field. I give a suitable example in the previous sessions. So, holding that example, holding that statement, I carry that statement. Because you know the definitions A not equals B not equals AB equal AB not equals 0, A not equals 0, B not equals AB equals 0, using a 0 divisor without a 0 divisor. When is the prime? When is n is not a prime form. By using the statement, by using the recalling the statement, we keep that statement. I prove in these cases. Yeah, A cross B equals 0, A equals 0, and B equals 0. Hence, Zn has no 0 divisor. Or it is an integral domain. Further, Zn is a finite set. This obvious. Zn is a finite set. Is a contain no number of elements. If n is a prime, then it has a finite integral domain. Therefore, it is a field. It is a field. So similarly, we using this definition, we come to the small that theorems. We come to the again one more theorem. Let R be a commutative ring. R be a commutative ring with unity. With unity. Then R is an integral domain if and only if R star means non-zero elements of R, non-zero. If you're not taking an element zero, not taking element zero, R star be a set of all non-zero element of R close under multiplications. Close under multiplication. Proof is simple. Proof is simple by using the zero divisor, without zero divisor, and integral domains like that. So let R be an integral domain. Let A comma B belongs to R star. R star means A not equal 0, B not equal 0. The product in that case. A not equal 0, B not equal 0. This implies AB not equal to 0. Since R is an integral domain, this implies A into B belongs to R star. Thus, R star is closed under multiplications. So, it's obvious. It's a zero divisor. Without a zero divisor. It's a zero divisor, the product should be a 0. Without a zero divisor, A not equal to 0, B not equal to 0, AB not equal to 0. Because we are choosing an element R star. R star means non-zero element of R. Non-zero element of R. The product should not be a 0. For example, Z7, Z3, Z5, Z11, Z13, like that. If a prime, this is closed under multiplication. Conversely, in the other side, only if conditions, let R star be a closed under multiplications. Therefore, for all A comma B in R star, this implies A into B in R star. That is A not equal to 0, B not equal to 0. This implies AB not equal to 0. So this is obvious on the using the first statements is in the sufficient statement form that A not equal to 0, B not equal to 0. The product should not be 0. Therefore, R has no zero divisor, and hence it is an integral domain. It is an integral domain. So Zn under addition, under multiplication, whatever will be, is a field when if and only if n is a prime form. N is a prime. So yes, again is using a theorem of the form. It's an integral domain. The non-zero element form a semi-group with respect to multiplication. We know semi-group means only two property hold. Closure property, associative property. Closure, associative. A closure and associative property. If you take any two elements, let R be an integral domain. A comma B in non-zero elements in R star. The arbitrary, this implies A not equal to 0, B not equal to 0. This implies AB not equal to 0. Yeah, similar same use regarding the because R is an integral domain. Therefore, R star is closed under multiplications. So, yeah, the multiplications plays an important role regarding whatever the BP field because the field is a multiplications order. So, for example, 2 is there, 1 by 2. So, 1 by 2 is a multiplicative inverse of 2. So, multiplicative inverse, that is, if the product is a non-zero, is a product we get in that. So simple. So if we go for that Z5, Z7, if we take this all these elements regarding that, if we take multiply 1, 2, 3, 4, 2, 3, 2, 3 is a 12. We can write 12 can be written as 2. So again 2, 3, 2 into 3 equal to 6. You can written as 1. So here 2 is the inverse of 3. 3 is the inverse of 2. So again 1 into 2 is 2. 1 into 3 is 3, 1 into 4 is 4 is a. So 2 is non-zero, 3 is non-zero. The product should not be 0. We are choosing that. Simple example Z5, Z7. If we analyze yourself, if analyzing yourself, if you're choosing any elements, commutative A into B equal to B into A, so unity is there. If you're choosing analyze yourself, if you take a non-zero element, inverses exist, this is a field. So we already previous sessions, session 3, 4 example, not that, but use why I'm taking example here. Now is clearly understood what is the number of the form. Right? the set of number of the form b root 2. B root 2. So b root 2, here b is a rational. B is a rational. We have 3 root 2 belongs to a, 3 root 2 belongs to a, and 5 root 2 belongs to a. See, the element of a is in the form of a root b. A root b like that, or whatever may be, 3 root 2, b, 5 root 2, elements of the form that. So I take a product, 3 root 2 into 5 root 2. What's the form? So 30, 30 into 30, 50, 30, 30. So now 30 cannot be written in the form of b root 2. 30 cannot be written in the form of b root 2, where b is a rational numbers. Therefore, 30 does not belongs to a. Thus, a is not close with respect to multiplication. Simple examples. Why I am saying this kind of example? What field you are choosing belongs to that same field. By giving this is a this idea it is giving. So if you are thinking like that, so this is happen, this is not happen like that. So what field, what number you are choosing, the product, the difference, the product, whatever may be, these are belongs to the same form, same form. But 30 cannot be written in the form of b root 2. So this is not a field. Hence, thus a not a clause under multiplication. For one more example, it's a simple example. Let n be set of all a positive integer, natural number. Since the integer 0 does not belongs to n, therefore additive identity does not exist. So n is not bearing. N is not bearing. So I given a slide. In the session 1 or 2 sessions, n is close addition and multiplication, but does not hold in subtractions or divisions. This is an examples. This is analysis in examples. I am saying this analysis in example does not hold. This is a proper way to write what field is formed. Resulted is in the same form. Resulted is in the same form. Then we get an idea of what is the field. It's not a field. What's the ring? What is conditions? It's a commutative, as a unity, as a multiplicative inverse. Each non-zero element has multiplicative inverse. Now we get the difference between what field, what's not a field. But that is the idea. We are using the reference of these books in Erskine, Perle, Michael Ortins, and Joseph.